So now let's build an equation to predict points scored using some common baseball statistics. So our dependent variable would now be points, and our independent variables would be some of the common baseball statistics that we have in our data set. So for example, the number of 2-point field goal attempts, the number of 3-point field goal attempts, offensive rebounds, defensive rebounds, assists, steals, blocks, turnovers, free throw attempts. We can use all of these. So let's build this regression, call it points reg. And that'll be equal to lm of points, regressing on all of those variables we just talked about. So x2pa, that's for 2-point attempts, plus x3pa, 3-point attempts, plus FTA, free throw attempts, AST for assists, ORB for offensive rebounds, DRB for defensive rebounds, TOV for turnovers, and STL for steals. And let's also throw in blocks, BLK. Okay, and as always, the data is from the NBA dataset. All right, so we've created our points regression model. Let's take a look at the summary. Always the first thing you should do. Okay, so taking a look at this, we can see that some of our variables are indeed very, very significant. Others are less significant. For example, steal only has one significant star. And some don't seem to be significant at all. For example, defensive rebounds, turnovers, and blocks. We do have a pretty good R-squared value, 0.8992, so it shows that there really is a linear relationship between points and all of these baseball statistics. Let's compute the residuals here. We can just do that by directly calling them points reg residuals. So there's the list of them. We'll use this to compute the sum of squared errors. So SSE is equal to sum of points reg $ residuals squared. All right, so what is the sum of squared errors here? It's quite a lot, 28,394,314. So the sum of squared errors number is not really a very interpretable quantity. But remember, we can also calculate the root mean squared error, which is much more interpretable. It's more like the average error we make in our predictions. So the root mean squared error, RMSE, let's calculate it here. It's just the square root of the sum of squared errors divided by n, where n here is the number of rows in the data set. All right, so we've calculated it, and it is 184.4. So on average, we make an error of about 184.4 points. That seems like quite a lot until you remember that the average number of points in a season is 8,370. So okay, if we have an average number of points of 8,370, being off by about 184.4 points is really not so bad. But I think we still have room for improvement in this model. If you recall, not all the variables were significant. Let's see if we can remove some of the insignificant variables one at a time. So the first variable we would want to remove is probably turnovers. And why do I say turnovers? It's because the p-value for turnovers was the highest, which means that it's the least statistically significant in our model. So let's create a new regression model without turnovers. So an easy way to do this is to just use your up arrow on your keyboard and scroll through your previous commands. Okay, so this is the command where we define the model. So now let's delete turnovers. Okay, and we'll call this points reg 2. So in our first regression model, points-reg, we had an r-squared of 0.8992. Let's take a look at the r-squared of points-reg 2. And we see that it's 0.8991. So almost exactly identical. It does go down, as we would expect, but very, very slightly. So it seems that we're justified in removing turnovers. Let's see if we can remove another one of the insignificant variables. And the next one we'd want to remove would be defensive rebounds. So again, let's create our model, taking out defensive rebounds, and calling this points-reg 3. Again, let's look at the summary to see if the r-squared changed. It's the same. So I think we're justified again in removing defensive rebounds. Let's try this one more time and see if we can remove blocks. So we'll remove blocks and call it points-reg 4. Take a look at the summary of points-reg 4. And again, the r-squared stayed the same. So now we've gotten down to a model which is a bit simpler. We've removed 3 insignificant variables and left only variables in the model that are significant. We've still got an r-squared of 0.899. Let's take a look at the sum of squared errors and the root mean squared error again, just to make sure we didn't inflate those too much by removing those variables. So remember that the sum of squared errors that we had in the original model was this giant number, 28,394,314. And the root mean squared error, the much more interpretable number, was 184.4. So let's calculate the sum of squared errors of this new model, points-reg 4. And let's call this sum of squared errors 4. So that will be the sum of points-reg 4, points-reg 4, $ residuals squared, and the root mean squared error 4 will be the square root of sum of squared error 4 divided by, again, the number of rows in the data set. All right, so let's take a look at these. The sum of squared errors here is now 28,421,465. Again, I find this very difficult to interpret. I like to look at the root mean squared error. So root mean squared error here is 184.5. So although we have increased the root mean squared error a little bit by removing those variables, it's really a very, very small amount. Essentially, we've kept the root mean squared error the same. So it seems like we've narrowed down on a much better model because it's simpler, it's more interpretable, and it's got just about the same amount of error.